Alright, so in this example physics problem, it says a car starting initially at rest uniformly accelerates to 20 meters per second over a distance of 300 meters. What is the car's acceleration? One of the words I catch very early is I see the word uniformly accelerates. I see initially at rest. It eventually goes to 20 meters per second at a distance of 300 meters. What is car's acceleration? Let's start with this very important statement. Uniformly accelerates. What that says is that the physics for this is constant acceleration. That's what the word uniformly means. Constant. And that means kinematic equations are valid, and I can use that to solve this problem. You have to figure out the fundamental thing in order to understand the game you're playing. Are the kinematic equations true? You have very few things early on in the semester that you can do, but by the end you'll have a lot of different tools, and you'll have to know which tool to use. You don't want to be trying to drive in a nail using a screwdriver. You don't want to try to drive a nail in using a circular saw. You don't want to try to mop a floor using a sewing needle. You must use the right tool for the right task. Here, the kinematic equations are valid. And that's great because they're useful. If they're true, I can do a lot of stuff with them. Now, I'm going to want to draw a picture. So here's my axis. And initially, I'm going to say that the car is at 0 meters. And it says initially it was at rest. So I know something else. I know v sub x naught was 0 meters per second. Now, a lot of you may only put v naught. That's okay. In one-dimensional problems at this point, there's no question that the direction that we're talking about here is the x direction. We're not moving along y. But in later problems, you'll have motion in both y and x. And when you put down something like velocity at t equals 0, you need to tell them, are you talking about the total velocity? You're talking about only the part along x, or only the part along y. Here, the part along x is the same as the total part. But in chapter 3, for instance, of Giancoli, it is not. So I just like to keep one notation throughout. The velocity going in x at t equals 0 was 0. Some later time, at a location of x, it says 300 meters. It says he's going to now be covering in the x direction, so v sub x, no 0 because it's a later t, 20 meters per second. Notice the big letter tells you what it is, a velocity. The little letters tell you which direction and when it's measured. X at some time. X at time 0. Now, when you do kinematic equations, it's good to build a little chart. There's x naught. You'll need to find the final position. You'll need to know the initial velocity. You might need to know the final velocity. You'll need to know the acceleration and the time. These are the only things that can show up in the problem. In our thing, we know the following. We're originally at 0. We're going to end up at 300 meters. We're initially moving at 0 meters per second. We're eventually going to be moving at 20 meters per second. We don't know the acceleration, and we were not given the time. There's two things that we can be asked in this type of problem to solve. Only two. The equations that are known to be true are the following. X is the initial position plus the initial velocity times time plus 1/2 the acceleration times time squared. The final velocity is the initial velocity plus the acceleration in x times time, and the final velocity squared is the initial velocity squared plus 2 times the acceleration times the change in the position. These are the three kinematic equations. 3 of them, so there's more than one way probably to solve since we only have 2 things to solve. Now, the first thing I like to do is I like to simplify my equation. So anything that's 0, I like to put it in. So that's gone. This term is gone. This term is gone. This is gone. This is gone. And I can see that good enough. I don't need to rewrite it, but if I couldn't, I'd need to rewrite the problem. If you've done a good enough job, you should be able to take the problem and move it off. So the only thing you have is that table and those equations, and you should be able to solve it. You should never need to look at the problem again. If you have to look at the problem again, you did not set the problem up well. Now, this problem says to find AX. Let's start with this equation. It has an AX in it, this equation, and this. So all three of them are possibilities because all three have AX in it. If I did this problem with this equation, do I know X? Yes, 300 meters. Do I know 1/2? Yes. Do I know AX? No, I'm looking for that. Do I know time? No, I don't know that. I have one equation but two unknowns. So by itself, you can't work the problem. Let's look at this one. Do I know Vx? Yes, 20 meters per second. Do I know AX? No. Do I know T? No. Two equations for one thing. But two unknowns and one equation here. This equation has the same two unknowns. I could combine these two equations, solve this for T, substitute it in, and solve for AX. A perfectly valid approach, one that would get full credit. But boy, that seems like that's really hard. That's going to be a lot of work. Maybe there's an easier way. Let's look at this equation. Do I know Vx? Yeah, 20 meters per second. Do I know 2? Yes. Do I know AX? I'm looking for that. Do I know X? Yeah, 300 meters. This equation only has one unknown. I could just solve it directly with no substitution. That sounds like an easier choice, so that's what I would do. But either approach would have been right. So Vx squared is 2a sub x times the position. Solving for a sub x, I get Vx squared over 2 times x. And on top, 20 meters per second squared. On the bottom, 2 times 300 meters. I have a meter squared divided by a meter gives me a single meter on top, and I'm divided by a second squared. So I end up in meters per second squared. That's the right unit. So check my units. If I was to increase the final speed, it makes sense the acceleration would have to be greater. If I did it over a longer period of time, it makes sense the acceleration would be littler. This equation seems to make some sense. I don't just work without thinking. I'm constantly checking before I go to a lot of extra work of solving a problem to see if what I'm doing makes sense. Plug in some numbers now. On the top I got 400 over 300, that's 4/3. Divided by 2, that's 4/6. 4/6 is 2/3. 0.667 meters per second squared. Could you do that without a calculator? You should be able to. No one's born with it. The ability to do these things is by practice, practice, practice. Make sure you're solving problems in a way that will make you better. We're not doing the problems just to get through. We're doing the problems so that in our careers we're going to be good at this, and it's going to enable us to get better careers and do more with it and be able to solve really interesting problems. This is like lifting weights. This isn't the end of the game. Nobody's hiring you to solve this car problem. What they're going to solve you is to solve a new medical technique, or to find a new way to get people from one place to the other, or develop a new bridge, or find a new building. This is just the practice that enables you to do those type of harder problems in your future. Alright, that solves this problem. By the way, I could put that in for A. If you now wanted to find T, I could go back here and say, hey, I know Vx, yes. Right, I could just put that right in here. And I'd say, yeah, I know Vx, that's 20. Do I know Ax? Yeah, that's this. Oops, sorry, didn't put in the right units, though. And then the only thing I wouldn't know is time, and then I could find time. And by the way, after you found the time, I could go back up here, and this equation, if I put in the A and the T, better work out. That's a check of my work. If you can't find a way, if you're stuck in a problem, and you can't find the thing you were asked for instance, you were asked for T, but you couldn't find it, but you could find A, solve it, put it in your table, and start the process over again. If you eventually fill up the whole table, you have worked the problem. It may not be the quickest way of working it, but you will have gotten an answer. It is better to have gotten an answer through hard work and sweat than it is to just say, oh, I can't work it, and stop. Nobody wants to hire a person who just gives up. All right, just like the football coach don't want a player who, when he runs sprints, quits. All right, they want the person who can persevere and work their way through it. So make sure you develop that habit, that you can persevere and work your way through a difficult problem in a systematic approach. What's neat about these is if you get good, there's never more than about 3 or 4 different problems. So by following this approach, if you do 400 problems, you've probably done each type of problem 100 times. So you're getting really good at it. If you hunt and mess and guess about a method and just randomly stick stuff in, then when you work 400 problems, you've worked 400 different problems, and you've worked each one only one way, one time, and you're not very good at it. Systematic problem solving is the way to become really good. Learn to set problems up, learn to step through, learn to think logically about what it is that tells you that each one of these lines is true. All right, that's what you have to be able to do to be good. If you try to shortchange it, you're eventually going to get bitten. All right, so practice, practice, practice. All right, that takes care of this example.